What specific problem does the proposed method aim to solve in the context of monocular depth estimation, and why is it crucial to address this issue?
The proposed method aims to solve the critical flaw in the inference pipeline of existing conditional latent diffusion models, particularly Marigold, which leads to poor single-step predictions in monocular depth estimation. This issue is crucial to address because it has been shown that the flawed inference results can mislead conclusions about the performance of diffusion-based models, causing them to be perceived as slow and inefficient. By correcting this flaw, the method enables high-precision single-step inference, significantly improving the speed of depth estimation by over 2,002 times, making it competitive with state-of-the-art discriminative models. Furthermore, this correction allows for efficient end-to-end fine-tuning and the application of advanced techniques like self-training with pseudo-labels, enhancing the overall performance of depth estimation tasks. Thus, resolving this problem not only boosts efficiency, but also opens new avenues for improving depth estimation methodologies.
How does the proposed method work? Illustrate step by step the modified inference pipeline that corrects the flaw in Marigold's approach.
The proposed method corrects a critical flaw in Marigold's inference pipeline by aligning the time step with the noise level during single-step predictions. First, the original implementation caused the model to receive an inconsistent pairing of time step and noise, leading to nonsensical predictions. The modified inference pipeline begins by fixing the time step to ensure it corresponds to the expected noise level, which is crucial for single-step inference. Instead of sampling the time step, the model is trained to always predict based on a fixed time step, allowing it to convert pure noise into a clean depth prediction effectively. This adjustment enables the model to produce sensible predictions in a single inference step, significantly improving efficiency and performance compared to the flawed original approach.
Can you provide a simple illustrative example of how the proposed algorithm processes an image to produce a depth map? Walk through the steps using a hypothetical input image scenario.
The proposed algorithm processes an image to produce a depth map through a series of well-defined steps. First, it takes a monocular input image, which could be a scene containing various objects, and feeds it into the modified Marigold model. The model, utilizing a fixed inference pipeline, generates a single-step prediction by aligning the time step with the noise level, ensuring that the model receives the correct input for depth estimation. This step effectively transforms the input noise into a latent representation that corresponds closely to the expected depth map. Finally, the output is decoded using a variational autoencoder (VAE) decoder, resulting in a clean depth map that accurately reflects the depth information of the original scene. This process is efficient, as the end-to-end fine-tuning allows the model to optimize directly for depth prediction, yielding high-quality results comparable to state-of-the-art methods.
What are the theoretical or practical benefits of achieving single-step inference in the modified Marigold model over traditional, multi-step inference processes?
The modified Marigold model achieves significant practical benefits through single-step inference compared to traditional multi-step processes. Firstly, it enhances efficiency by being over 2,002 times faster, which is crucial for real-time applications. Secondly, single-step inference allows for efficient task-specific end-to-end fine-tuning without the need to backpropagate through multiple network invocations, simplifying the training process. Additionally, it enables the application of advanced techniques like self-training with pseudo-labels, which were previously challenging to implement with multi-step models. Finally, the corrected inference pipeline ensures that single-step predictions are comparable in quality to multi-step outputs, thus maintaining high performance while improving speed.
What experimental design was used to validate the new method, and what specific metrics were employed to measure its performance against existing methods?
To validate the new method, the experimental design involved fine-tuning the Marigold model end-to-end into a deterministic affine invariant depth estimator for monocular images, using a scale and shift invariant loss function. The performance of this fine-tuned model was compared against existing diffusion-based depth and normal estimation methods, as well as state-of-the-art discriminative models. Specific metrics employed to measure performance included least squares fitting for depth estimation, which estimates scale and shift values, and an angle-based loss function for surface normal estimation, which evaluates the angle between ground truth and predicted normals. The results indicated that the fine-tuned models outperformed current state-of-the-art generative methods for depth estimation on most datasets, and set new state-of-the-art results for surface normal estimation across all evaluated datasets, except for one. This comprehensive evaluation demonstrated the effectiveness of the proposed method in comparison to existing approaches.
What limitations or potential drawbacks of the proposed method have you identified, and how might they affect its application in real-world scenarios?
The proposed method, while demonstrating significant improvements in efficiency and performance for monocular depth estimation, has some limitations. One potential drawback is that the fine-tuning process relies on a small dataset of high-quality synthetic labeled data, which may not generalize well to diverse real-world environments. Additionally, although the fixed inference pipeline enhances single-step predictions, the initial implementation flaws could lead to inconsistent results if not properly addressed. Furthermore, while the method outperforms existing diffusion-based models, it still faces competition from discriminative methods like depth anything and metric 3D, which are trained on much larger datasets, potentially limiting its applicability in scenarios where extensive training data is available. Lastly, the reliance on specific loss functions, such as the affine invariant loss for depth estimation, may restrict the model's adaptability to other tasks or datasets that do not conform to these assumptions.